Hello and welcome back to the lab. Today on the bench we have the humble capacitor. In this video I've gotten a lot of requests about selecting capacitors, how I pick the capacitors I pick, why I pick the capacitors I pick. I've gotten questions about ESR, EPR, dissipation factor, quality factor, things like that, and so I told everybody I'd make a video about it. That is this video. My goal of this video is to keep a intermediate discussion of capacitors. There's a lot of back to basics videos and things like that out there with a lot of good content about basics of capacitors. So I'm going to try to go a little bit deeper than that, and that's my target. If anybody has anything to add, or if this video generates any more questions, feel free to leave them in the comments below, and we'll see if we can't demystify the humble capacitor. I am going to specifically keep this video to electrolytic capacitors and polarized capacitors because that's what I'm getting the most questions on. Some of this information applies to all types of capacitors, but given doing restorations and things like that, electrolytics give us the most trouble. That's what we're going to stick to today. So first things first is choosing a capacitor and sourcing a capacitor. So in these two particular examples, I have two Nichicon capacitors. This one is a 450 volt, 560 microfarad. This is a 10,000 microfarad, 25 volt capacitor that I used in my, actually I think this guy has to go into the 576 because this is on, I believe this is one of the ones that's on the 5 volt rail. So the first problem is, where do you order a capacitor from? So there's a lot of counterfeit components out there. There's a lot of straight up fakes. Always be sure who you're ordering from. My main suppliers in the lab are the three big ones from DigiKey, Mouser, and Arrow. I'm not saying that's the only ones, and none of them have sponsored any of these videos, but that just seems to be some reliable sources of components. I have sourced components from auction sites. I have sourced components from large online vendors that don't specialize in electronics parts. I've also sourced, there's a couple of tube suppliers that I use that are not the three big ones for some select components, tubes specifically. If I have some musicians that send me amplifiers to work on regularly, and I need a source of new tubes. So some of them specify they want brand new, not new old stock, just new tubes, and so I do have to source those. For bulk filtering, pretty much everything uses an electrolytic capacitor, depending on the unit, some things like that. Even some nice scientific gear. My PM100 is a perfect example of that. I did not do a video on that restoration because I restored that before I was on YouTube. It needed every electrolytic capacitor in the entire unit replaced. They were all bad. The unit was out to lunch, it was reading overflow, things like that. I replaced all the caps. No problem since. Just noise on the power rails was causing the chips to go kind of bonkers. And that is not an inexpensive piece of gear, and I open it up and they use 85-degree C caps. That gets into one of the criteria that I use for selecting capacitors. I don't care what the application, at least for me, I don't care what the application is. I'm not building things in the order of millions and down to a price. I don't buy anything that's less than 105 degrees C if I can help it. There are some instances where I've absolutely needed a capacitor that was a physical package. I had to have the size to fit it, and I could only get it in an 85 degrees C. So I had to go with it because it was the only way I could get it fixed. Now, when selecting capacitors, as long as the physical package size doesn't matter, in modern capacitors, the voltage doesn't matter. I should say the voltage doesn't matter as long as it's higher than what the rail is. Some of the old Tektronix gear has gotten the tantalum capacitors that they put in the Tektronix equipment has gotten a bad rap because they have failures. Well, one of the main reasons they have failures is the bulk filters dry out. They have a 15-volt rail with a 16-volt cap on it. This guy goes bad, ripple hits the rail, all of a sudden you're above the rated voltage of the cap, and the tantrum, however you want it, tantrum cap, they go bad, that's it, and they actually explode. They get very cranky. Electrolytics, if you overvolt them, they will vent. That's actually what the vent stamp is on top, and they'll pop, and it's not a good day either. So, but even if I had 16 volts in a modern capacitor, I can use a 450 volt, and that's totally fine. No problems. Now, I'm probably going to catch a little bit in the comments about that because everybody will be like, oh, well, you'll wreck the cap, things like that. And it has to do with dielectric absorption, or not dielectric absorption. You'll permanently decrease the working voltage of the capacitor. In older, the big silver multi-can caps, that is true. But it's because the dielectric in there is caustic. It actually eats away at the, or I'm sorry, not the dielectric. The electrolyte is caustic. It eats away at the dielectric, thins it out, and reduces the working voltage. That's actually what people talk about when they say they're reforming a capacitor, is building up that dielectric back. And capacitors that sit on the shelf and aren't even in a piece of gear, that the electrolyte is chewing on the dielectric just chemically as the capacitor just sits on the shelf. So if you volt slam a capacitor where you take this 400, let's say this is an old, hypothetically this is an old capacitor, take this, put it in a unit, hit it with B+, the dielectric's nowhere, it could blow the capacitor short just because the dielectric's not thick enough to hold back that voltage. And that's what the reforming process is, where it brings the capacitor up and reforms it. Now, in the gear that I have in the lab, people may think I'm heavy-handed because I do replace a lot of electrolytics and things like that. Well, in like the 576 curve tracer, I want to take no chances because, like the high voltage transformer, it's a unique part. If that blows out, I will have a very hard time finding another one. So I will give it a fresh capacitor. I don't mind the couple dollars, even up to like $6, $7 a piece. Sometimes with the high voltage, high value caps, they can get. Actually, they can go up from there. One of the most expensive capacitors that I've ever run across was a hermetically sealed, high value tantalum capacitor, and it was 4 figures. Like $1,500 per cap. Like, it was insane. Needless to say, I did not source any of those. But the dielectric reforms and regrows, and as long as the capacitor's not overcurrented during that time period, it will end up being okay. Unless the capacitor's faulty, dried out, something else. Modern caps, they don't use a caustic dielectric or electrolyte. I keep saying dielectric. They don't use a caustic electrolyte, so they have less of that problem. Now, there is still a reformation period, even with modern capacitors, which I can actually show on some of my equipment. If you look at the leakage current through the capacitor, it'll peak and then it'll come down and then level off at a value. And actually, the data sheets, to get the leakage value in the data sheet, there's a procedure where they say you have to bring the cap up to the working voltage. It has to be there for so long, and then you can do a leakage test to make sure it's in specification. Even the manufacturers are counting on a mild reformation process to bring the capacitor back into spec. Physical size difference. Obviously, this has a higher capacitance, but it's a lower voltage. The voltage and the capacitance dictate the size of the capacitor. More so the voltage. If this was a 560 microfarad 25 volt capacity, it would be tiny compared to this one, because this one has to hold back 450 volts. But as long as they'll fit, you can use a higher voltage capacitor in a lower voltage application. They just they'll last longer. They're not worked as hard, things like that, so they have a more longevity to them. So in terms of sourcing, I will look for a similar capacitance, always going over if I have to. If I can't find the exact capacitance, go over. Also, depending on the application, I might bump it up just a little bit, and I'll get into that, why I can do that here when I get a parts list. And then you can always overvolt an electrolytic. You cannot undervolt an electrolytic. If you undervolt an electrolytic, it will explode. It will get very unhappy in circuit, and it will be a very energetic reaction, smoke out the lab, if not blow the capacitor up. You put this guy on a 450 volt rail, it will literally throw shrapnel around the lab as it goes off. It's not going to like it. Okay, here's the parts list for a Type 576, and I'm going to zoom in on a couple of specific examples that I want to call out. I have these two up here, and then these two down here. So we'll take a look at the ones up here first. As we can see, the specific capacitor doesn't matter. This happens to be C30, 326, and 329. They are fixed electrolytics, non-adjustables. I don't know why they call out fixed in the documentation. However, like this one is a variable capacitor, so if it's not an adjustable cap, it's going to be fixed. It is an electrolytic, and this one is a 1000 microfarad at 25 volts. Now, one of the things you'll notice is the tolerance of the capacitor is plus 75%, minus 10%. So this is saying that the circuit can take a lot higher capacitance, but you don't necessarily want to go much lower because you need at least 1000 microfarads. Same thing for this one. This is a 5200 microfarad, but it's plus 75 minus 10. So the tolerances on these capacitors is actually pretty huge versus a modern capacitor, which is plus minus 20%. So back when these machines were built and constructed, manufacturing tolerances were nowhere near as good as they are today. And so capacitors, when you ordered one, you'd order a 1000 microfarad, and if it was 1750, that would be in spec. if it was a 9990, that would be in spec. So the manufacturing tolerances were actually really wide. This is also one of the reasons why a lot of high precision stuff that was made back then is select on test. So they'd measure and then bin the capacitors so they would be able to select one, especially when tuning like oscillator circuits, things like that. So that the capacitance is actually important. But so there would be it would be someone's job to test every single one of these as they came in the door. And then they'd say, this is good, this isn't good, things like that. You'll see, as you look through the replacement parts, you'll see a lot of that in some of the tech stuff where it'll say this is a 2N3906 transistor, but it'll say select on test. So there's a critical parameter that they're looking at for that transistor, and they selected it for that. Bulk decoupling electrolytics, nobody really did that. The other two I wanted to call out is these down here. There's one on there. They are. Is these two. This 1100 microfarad is a plus 100% 15 volt cap. So this can be double what the value is listed here, and it would still be fine for in circuit. This particular 4200 microfarad is also double what would be in spec. So going, if you can't find an exact match and you're trying to get a unit up and running, going a little over with a plus 100% tolerance is not going to hurt anything at all. If this was a 4700 microfarad, totally fine. You can overdo the capacitance, especially in tube gear and things like that. Now you can also burn up silicon diodes and stuff like that too in the rectifiers if you put too large a bulk filtering cap in a circuit. So you have transformer, bridge rectifier, filter cap. You can actually current slam the rectifier because when you first flip the unit on, it has to charge this cap, and if this cap is too big, you can see a temporary huge current spike that it pulls through the diodes. I do know some people who have burned up rectifiers because the rectifier was only good for 2 amps, but they found out the surge current when they were charging the big caps that they put right after the rectifier to quiet the power supply were drawing like 6 amps of current for like 25 milliseconds. Not a lot, but when you first flip that on, these caps are dead. They're dry. Well, not dry. They're empty. They got to get filled up. So they suck all the current they can through the rectifier. And that is something you want to keep in mind because it may work in the board. It may work. This particular example that I'm remembering worked for the gentleman for 6 months. And then all of a sudden the rectifier died, blew a whole bunch of expensive boards up when the diode shorted. But it worked for 6 months. So it got into test, got out of test, did everything. But they found out the surge current was way over what the rectifier could take, and it was hitting it every time they turned it on until it finally gave up and failed. So rectifiers should also be rated for the surge current, not the running current. That's why sometimes I haven't done a lot of from scratch builds. It's been a lot of repairs on the channel, but if a 2 amp rectifier's good, a 6 amp rectifier running at 2 amps is better. So I don't like running parts right up to their limits. I like having an overhead just for fluctuations, things like that, and because when I build stuff, I like it to withstand the test of time. So I always overbuild, probably more than I should, but I don't. Again, I'm not building for millions, so spending an extra $2 or $3 on a build, it doesn't hurt my feelings at all if I never have to repair it. Okay, now we're getting into some of the math. Don't run away. I promise this is not as complicated as it looks, and it will be a lot simpler once I explain it. I don't necessarily care what all this math means. But I got asked about Q for quality factor, D for dissipation factor, and a few other things, and then we'll talk about ESR and EPR. There is one thing, and I've scanned a copy of this write-up, and I will post that. I believe I can make a post for everyone to grab from Patreon, but I'll make an open post to Patreon with this sheet on it, so I apologize for the chicken scratches. However, the important part is I have to do a definition first, is I need to define X of C, which is the reactance of the capacitor. So for just going through it real fast, it's 1 over 2 pi the frequency times the capacitance. The real important part when running through these equations is, and the one thing to keep in mind, which I think gets lost in some of the definitions in the math, is the way this is written out, Greek symbol for delta. We have F up here, which is for the frequency, but then some of the formulas also have W or W naught or W0 for the frequency as well. Now, that's really important because if you take a look at some of these formulas, don't need to understand them, just keep in mind, here, 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 everywhere that I've highlighted in these formulas, this all has a frequency component. So what we're going to talk about, the quality factor of the capacitor, the dissipation factor of the capacitor, the loss tangent of the capacitor, which is also the dissipation factor of the capacitor, all of this is frequency based and will change based on frequency. So it will be completely different for a filter capacitor in a power supply than it would be in an oscillator circuit. Well, there won't be any electrolytics in an oscillator circuit. You wouldn't do that. But timing capacitor. So it would be completely different for a bulk filter for a power supply than it would be for a timing capacitor. And I will show that because that's one of the questions that I got asked. So the quality factor and the dissipation factor of the capacitor are actually the same thing. It's two ways of looking at the same thing. You can see quality factor is 1 over WCR and the dissipation factor is 1 over WRC. Now, because these are being multiplied, you can write this WCR. That is exactly the same thing. So quality factor and dissipation factor are actually the same parameter in different situations. Now, what is that? The dissipation factor is how much power is dissipated in the capacitor as heat. So essentially it is I don't want to say the resistance of the capacitor, but it is an energy conversion to heat inside the capacitor itself. So if you use a capacitor at the wrong frequency, it can have a very high dissipation factor where it has a lot of internal heating, and it's not the right type of capacitor or the wrong value in the circuit. But the dissipation factor is how much heat is generated in the capacitor while it's in circuit doing its job. Primarily looked at in power supply filtering capacitors, and it also ties into equivalent series resistance, the ESR of the capacitor, because the higher the ESR, the higher the dissipation factor. Because as you can see, the loss tangent of the capacitor, which is tangent of delta, is the dissipation factor. But that same tangent of delta is the ESR over the capacitive reactance. So there is an ESR component to dissipation factor. ESR, and also the dissipation factor, will be exaggerated by the amount of current that's being pulled out of the capacitor, because it has to pull the current through the ESR, because the ESR is capacitor to a resistance, which will turn power into heat and then out. So the more current you pull from the capacitor, the larger of an effect the ESR has on the capacitor's internal heating. That's one of the reasons why I also like to overrate the capacitors a little bit, because the overrated the capacitor, the less internal heating they have, and the longer they stick around without needing to be changed. Selecting the wrong type of capacitor for the job, because there's a frequency component in there, can exaggerate the ESR. For example, a large electrolytic in a high frequency circuit, it's just not going to work very well, because it wasn't designed for high frequency work. Also, large capacitance in high frequency circuits is another problem. A good way to define ESR is how easy it is for the capacitor to deliver energy into the circuit and take energy out of the circuit. So especially in a rectifier, a filter capacitor for a power supply, the less current you draw out of the capacitor, the less the ESR matters, because it's not showing up as much, because there's not a lot of current being drawn. But there are also times where ESR is not the important parameter. I got a question from a viewer about some timing capacitors with ESR. Yes, they read a high ESR, but that's not what they were for. So even though they read a high ESR, those timing capacitors were not faulty. They were working just fine. So ESR's not the only parameter that is a concern. Leakage across the capacitor is EPR, or equivalent parallel resistance. So this is modeled where you have VCC and ground. There will be some leakage current through the capacitor as it's in operation. This is really driven by what the dielectric is on the capacitor. The better a dielectric, for instance, a silver mica is probably the best in terms of leakage. The problem is getting a silver mica in these capacitance values. The capacitor would be enormous, if not impossible to build. So we do have to accept some EPR with an electrolytic capacitor, because it's just the nature of the way they work, and it's just living in the real world instead of the ideal. So this would be when I would put if I put a 15 volts, call it 15 volts at VCC, the current that at steady state would just be drawn through the capacitor. Now, I'm not pulling any current from the capacitor. This is just what's passing through the capacitor in real time. I'm going to show this with the source measure unit here in a little bit. We'll hook it up to the capacitor, let it charge up, and then we'll watch as it reforms. We'll reform the dielectric, then I'll up the voltage and show it reform the dielectric again. That will take some time, maybe even overnight, and this is a brand new capacitor, so there will always be some leakage. Now, in power supply circuits, things like that, does the EPR matter? No, ESR is the more, on the filter caps, ESR is the bigger parameter. However, there's always a little bit that squeaks through and ends up to ground. If this runs away, the capacitor turns into a resistor and it just overheats and bad things happen. So this is a parameter to be aware of. And in some circuits it matters, in some circuits it's not. It doesn't. One other thing of note is when I was talking about tolerances of the capacitors, putting an extra large capacitor in a tube power supply, you can actually do damage to the rectifier diode, or the rectifier tube. You will know because the rectifier will turn into a fuse and go away. So just don't overload rectifier tubes in tube circuits. Okay, I'm going to attempt to model some of this in the real world, and we're going to do some experiments. So I have my laptop set up. This is live. Move you guys off to the side so I can see this. So I have my laptop set up. Front panel controls. The output is currently off. This is set live for, like I can change to continuous measurement mode, and now we'll actually get some measurements. Let's see. I have the 560 microfarad cap hooked up. It's the 450 volt one. But let us source current and measure voltage. No. What I actually want to do is source voltage and measure current. Source voltage and why did you do that? Because I hit the wrong button like an idiot. Source voltage, measure current. There we go. So we're going to source. Let's give it 100 milliamps to start. So I'm going to charge this capacitor up current limited. We will source 10 volts. Now, when I turn the output on, the source measure unit is going to dump 100 milliamps into the capacitor until it reaches 10 volts. So what I'm going to do is, let's go to graphing mode. So now we have current on this side. So we have current on the vertical and time on the horizontal. So what I'm going to do is I'm going to clear the buffer, and then I'm going to trigger the output. And what we're going to see is we're going to see a spike to 100 milliamps, and then as the capacitor reforms, we'll see a slow drop off of the current going through the capacitor till it hits a very low level. What I'll do then is I'll bump the voltage to, I'll add like 5 or 6, maybe 20 volts to it, and then we'll actually watch it bump up and then come back down again, and they'll have another curve. That's the dielectric reforming in the capacitor at the new higher voltage. So let's run the experiment. So what I'm going to do is I'm going to set it to manual trigger mode. You guys can see what I'm doing on the front panel because it's showing up. What we'll do is we will set it to buffer. No. Clear active buffer. There we go. No data. Perfect. So now what I'm going to do is, let's do this at a high accuracy. So we'll do continuous measurement, blow up the graph, and hit the go button. So as we can see, right now the capacitor is passing 2.2, 2.3 microamps, and as time goes on, that's slowly coming down. Let's see if I can't get this graph out of here that I'm looking for, because I know it's possible. There it is. So that's our big spike in the beginning. Now what I'm going to do is I'm going to clear the buffer again. And we'll just let it pick up from here. Come on. We can start to see the trend. The line is leaning a little bit down. All right. So what I'm going to do is I'm going to just let this run, and then I will bring you guys back after this has run for a while. As you can see, the trend line is already starting to develop as it's coming down, starting to kind of curl down. I expect it to keep traversing down the longer I let it run as the capacitor reaches equilibrium at this voltage. Now, if you look, we've dropped almost a microamp through the capacitor already, so we are dealing with very small currents. Like, it's not a resistor, obviously, it's a capacitor, but the capacitor is still passing DC. So the source measure unit's a very clean DC supply, but a couple of microamps is still making it through. Now on my IT28, this would pass eventually once the capacitor was charged up. The reason it would pass is because the IT28 is set to indicate a leakage of more than 5 microamps on. It's calibrated to 5 microamps for the electrolytic setting. So this is completely fine. This would not be okay for a silver mica cap. That would be a leaky silver mica cap, but that gets into the dielectric. So I'm gonna let this run. One of the reasons we're not seeing a crazy amount of current, not crazy amount of current, but one of the reasons we're not seeing a substantial amount of leakage at the moment is because I'm hitting a 450 volt capacitor with 10 volts. So I can jump this up to 200 if we wanted to do that. As a matter of fact, we can. I'll have to be careful on the bench because this is going to be 200 volts direct into a capacitor. However, okay, we've just hit current limit while it charges, and now it's back. So let's check what the graph did. And we're drawing milliamps of current now. So let me clear the buffer here real quick. This will exaggerate more. This will exaggerate the graph more than what I'm trying to show. There we go. So now I've got 200 volts on that 450 volt capacitor. As you can see, our current through the capacitor went up. We have a leakage current of about 1 milliamp at the moment. Now that would be considered insufficient. This would fail, except this capacitor was sitting on the shelf. We didn't have it taken. We still haven't even taken this up to working voltage. I can't with this SMU. This isn't the high voltage one, so it tops out at 200 volts. I'm already at the top end of its capacity, or its power voltage curve. But this will show as the leakage settles off, and even a brand new capacitor reforms slightly as it goes. But I'm going to let this run, and I'll bring you guys back when the graph is filled out. Okay, as we can see from the readings on the unit, it's was a little lower, but it's kind of stabilized at about 6 microamps. It is a lot warmer in here given the weather. We started a fire, so that's some of what is going on. But here is the graph. So as we can see, during this reforming period, we had this very rapid decrease in current through the capacitor, and then it kind of just trailed off along the edge. So I don't know if this would get any better overnight, but that is good enough for what I wanted to show. And I want to discharge this capacitor and then hook it up to my 7510 to demonstrate another property that people should be aware of. Now I've moved the meter down to my 7510. I want a pretty fast rate on this one, so I'm going to let it kick over, but I don't want the charge to bleed off. We're actually watching the charge bleed off through the meter impedance right now, since we're not hooked up to the power supply anymore. But I don't want to do that completely because I want to actually discharge this more rapidly, because I want to talk about dielectric absorption. We had charge being pushed into this capacitor for the last couple hours or so, and one of the things that'll happen with that is the dielectric will soak some charge. So what I'm going to do, with hopefully not causing a bright flash and bad things happening, going to hit the capacitor with a 220 ohm resistor, and we're going to discharge it. So we'll see the voltage crash when I have the resistor hooked up. And then we will watch for the effect. There we go. Turn that back to auto. And we'll discharge this some more through this 220K resistor. So I've got about 90 millivolts on the capacitor. So I take the resistor away, and you can instantly see the voltage start climbing again. We're at 300, 400 millivolts. It's climbing pretty rapidly. So let's clear the buffer. And we'll go to the graph, and we'll just watch it climb. Now all this is, the capacitor, there's the meter, those leads go to the capacitor that's hiding behind the laptop, and nothing else. So there's no power supply, there's no nothing hooked up to this capacitor. And yet we see this, wake up, this linear voltage climbing. And we're at 1.5, 1.6 volts already. And this is real time. This isn't sped up. So I'm going to let this cook for a little bit. We'll see how high we get. But what this is this is charge coming out of the dielectric, since it's not being forced in anymore. And then it's just building back up on the plates of the capacitor. Now, you could get a decently high recovery voltage off of this, especially with a high voltage supply going in. So this is something to be wary of. So, and over time, it's pretty linear too. I mean, it's not like it's a huge. So you pull this out, you chuck it in a parts box or something like this. Capacitor's just building up charge again. So let's see how high this gets. Bear in mind, this is a 450 volt capacitor. We only had 200 volts into it, so we didn't even have it at its max voltage. But I'm curious to see how high it gets. Now, the meter in the 10 volt range has a very high input impedance, so eventually what will happen is we'll see it peak, and then it'll start discharging through the meter again, through the meter's input. But we'll see what happens. Yeah, we'll just take a look at the chart when it's done. Well, to be honest, I was expecting more recovery out of the electrolytic, but it did come back up. So on that note, we did get a little bit of dielectric absorption. Not as much as I expected, though. I expected at least probably better than 25, maybe 50 volts. But topped out at 6. Actually, as you can see, we're still going up slightly, but this is about as good as it's going to get. Now, on the complete other end of the spectrum, the output is on. We have a 440 40 volt, 10 nanofarad XY rated capacitor, and this is the leakage current with it on at 200 volts. There you are, 200 volts. So we're at 400 picoamps at the moment, dancing around. So different materials can yield drastically different results. So hooked up to the source measure unit, I have a extremely high quality capacitor. This is a Tektronix made timing capacitor. Actually, I have a set, timing capacitor set of, for a 465B, this is one of the timing capacitors out of it. And let me show you what I'm getting. Well, here's the high score for leakage for the day. This is that Tektronix made timing capacitor out of a 465. This is a 50, 60-year-old capacitor. 0.02 nanoamps for leakage. This is an incredibly good capacitor. These are also super high quality capacitors. I'll zoom in on them here in a second. This was the cap we were actually testing. It's a 9.95 microfarad at 25 working volts DC. I was testing it at 20. I didn't want to push this too far because I believe these are hermetically sealed wet tantalum capacitors, so overvolt, even though I was using a very precise voltage reference, wanted to give myself a buffer and not send it right up to its working voltage. I also don't know what these see in circuit on the timing board. I haven't looked in a while, so can't recall what they see, but here's a 35 volt, a 0.1 microfarad, 35 volt. So these are what actually drive the time base in a 465, and depending on the tests you run on these, they're going to show very good, but they're also going to show very poor. I just ran the DC leakage test, but if I run an AC test on some of these, depending on the frequency, they're going to show really, really bad ESR. And I will also show how that can be frequency dependent too. Is it a 9.85 or is it a 985? I can't tell. So this is a 9.85 picofarad capacitor at 100 working volts DC. So we're going to hook this up in the correct polarity. We're going to run some tests on it with the DE5000. It's the best LCR meter that I've got at the moment. I do have a Keysight LCR meter on the list of things to acquire, but funding limits that. So let's see, we're going to go to capacitor, and then we're going to look for we want capacitor series. There we go. And ESR. You can see the ESR is jumping around wildly, but I'm also seeing readings of 100 ohms of ESR. Now, to prove that this is frequency dependent, actually it looks like it's a 985, not a 9.85. But if I change the frequency, where we were at 1 kilohertz, seeing an ESR in the hundreds of ohms, we're now down to 14. Let's push the meter up a little farther. Oops. ESR. Frequency. So at 100 kilohertz, we're down at 1.78. So ESR, depending on the capacitor you're testing, can be very frequency dependent. This is also a cap where I wouldn't be worried about ESR due to these are timing caps, so ESR is less critical in these than it is for a filter cap and a power supply. For these, the ultimate capacitance is the controlling factor because they're in timing circuits. We'll go to the other side of the spectrum with a 1 microfarad, 35 volt. And we'll hook this up this way. Testing this at 100 kilohertz, we have 0.01 ohm of ESR, and we're pretty good. 1.03 nanofarads, or 1.03 microfarads, so we're pretty good there. But let's check what happens when we drop the frequency down. This one actually still tests pretty good. 100 hertz, 0.2, and our capacitance is still good. Yeah, this one's testing all right. Let's test that other small one. This is a 998 picofarad 100 volt capacitor, and this one I know the last time I tested its ESR, it was abysmal. So at 100 hertz testing, we're bouncing between 150. It's not stable because it's too low a frequency for this capacitor. So it's testing okay, 0.6, but then it'll go up to 150. Oh no, that's 0.6 kilo ohms. So that's 300 ohms ESR at this frequency for this capacitor. So at 120, 400 ohms of ESR, and the value's off. Because this isn't stable, it's still bouncing around, so this is still under the frequency for this particular capacitor. 10 kilohertz. Now we're starting to get into where the meter can start measuring a decent ESR on it. 100. Yeah, 2 to 3 ohms. So as you can see, ESR can be very frequency dependent. Now, even with those wild readings on the ESR tester, or the LCR meter, I have no reason to believe these capacitors are bad. These are actually all still good. These very rarely fail. The timing capacitors that Tech made, they didn't spare, since they're kind of the heart of the time base of the scopes. Tech didn't spare any expense on making these. They wanted to make sure they were going to last. So these are all still good. I'm going to keep these as a set. That's the other thing is, a lot of these are picked for absolute value at the factory. So when these scopes were built, and then these were all done as a set to keep the ratios together, to keep the different time bases lined up with each other within specification. So unless you're absolutely sure timing capacitors failed, leave them until they prove themselves to be bad, because getting the right ratios again to get the dials to line up is going to be a nightmare if you ever have to replace these, because they have to be replaced as a set. You can't just replace one. Thanks for stopping by the lab and taking a look at the intermediate discussion for capacitors and doing a couple of experiments. I do hope this cleared up more questions than it generated. However, if people still have questions, please leave a comment in the description, in the comments below, and I will see what questions there are and if there's anything I can do to help demystify some of this. As always, I will see everyone in the next video. Bye for now.